Section 3 is going to have two very distinct things that we'll be looking at. The first is going to be about false positives and false negatives. What this refers to is some sort of a test that's being conducted. Usually it's a medical test, and in this activity that's sort of how you're going to see it. We're going to be talking about mammograms, we're going to look at pregnancy tests, and I don't think we have any activity, but we could do like drug tests. So they're usually along the lines of medical things. Now, when a test is done, what we hope is that we're going to get accurate results from it. But there's four different things that can actually be a result of some sort of a test that's done. And those are these bullet points. So I'll go ahead and talk about these before I mention what's happening up at the top part. Okay, so suppose there's a test that's done. This is going to be about mammograms though, so we're thinking cancer. There's going to be a test that's done. There's two things that we really would hope that are going to happen. We either hope that we get a true positive test or that we get a true negative test. So a true positive test comes back with a positive result that the patient has cancer. That's what that says. A positive test says that the patient has cancer, and it would be a true positive if the patient actually does have cancer. So patient with cancer. Okay, the other one that we would like to see would be a true negative. We'd like to see a negative result meaning that the patient does not have cancer. We want to see that result from the test if the patient doesn't have cancer. Those are the ones we want. But then you've got these other two that are the wrong cases, the ones that we don't want to see and we always hope to minimize here. A false positive. A positive test result, test that says you have cancer, when the patient doesn't actually have cancer. Okay, when the patient is without cancer. We also have a false negative test that comes back and says no to cancer, but the patient actually does have cancer. This is sort of how we see things that are advertised a lot, especially we're going to talk pregnancy tests in a little bit, and you'll see in commercials all the time saying how accurate they are. And that's what this is sort of referring to. And what we want to get is an idea of what does that make us feel about the results that we would be getting? Like how much do we believe in those results? Okay, so it says here, assume that mammogram screening is 85% accurate in detecting malignant tumors and benign tumors as benign. Okay, so what it's saying is that if a person does have cancer, it 85% accurately notices that. It's going to miss 15% of those cases. It's also going to be 85% accurate for benign. So if you don't actually have cancer, 85% of the time it's going to come back correct, and then 15% of the time it's going to say that they do have cancers. That would be a false positive in that case. We pose this question to you. Do you think that this means that there's an 85% chance, so I should read this piece first. Suppose that a test comes back with a positive for cancer. Do you think that this means that there's an 85% chance that the patient has cancer? Well, yeah, that's probably what we would think because of the way that the information is presented to us in this simple manner that that the tests seem fairly accurate, right? 85% out of 100. It's not perfect, of course, and you'd probably want it to be closer to 100%, but it's in the higher end of it. So yeah, if a test comes back and says that you have cancer, then we're thinking, oh man, 85%. Yeah, that's probably accurate. I'll be lucky if I was one of those false positive tests. Well, it ends up when you really start looking at the numbers here, that even though it comes back and says that it's positive, there's only about a 5% chance. The reason for that is it's a bit tricky to explain here just in words, but we're going to start to see it in the numbers, and I'll try and keep coming back to it. When these tests are done, because like a mammogram is just a normal test that's done to women across the country, right? When that test is done, there's a lot of women who don't have malignant tumors. They don't have the actual cancer in there. So because there's so many that should test negative, there ends up being this high probability of getting false positives. When you throw in so many that don't have whatever it is that we're testing for, in this case cancer, if you even get a few back that that are false positives, it can throw off the data. And that's what we're going to see here a little bit later. So I know that part. All right, unfortunately, we're not going to be coming back to this part here and talking about that 5% from these cancer tests. The reason is we don't have the information on something that's called an incidence rate, which is the actual number of, or a percentage of the women taking the test that would have the cancer. So what we're going to do is turn our attention to another problem. Most of this stuff kind of parallels in there, so we'll still get the same discussion about that craziness and the percentages. All right, so what we have here is a pregnancy test that we're looking at. Two-way table that we had recently talked about with Venn diagram stuff. There's two things that we're looking at, and it creates, you can see here in the middle of it, you get your true positive, false positive, and all that stuff. There's two things that we're looking at. There's being pregnant and not being pregnant, like the real results, what's actually here. But then you've also got the test that goes with it. All right, and the test isn't going to always identify women that are pregnant, and a test isn't always going to identify women who are not pregnant. There's going to be these false positives, women whose tests come back positive but don't actually have, or I was going to say cancer, they don't actually have a baby. All right, so the whole thing has been sort of populated here. Now what I'm going to do is go back to the beginning and pull out some of the numbers that are important here. First, our total is going to be 500. 500 women were tested here. They give you this information that 50 of the women are actually pregnant and 450 of the women are not pregnant. And it tells us that the pregnancy test is 90% accurate. All right, so let's see how all those numbers would have gone into here. The 50 and the 450 are going to go down to the bottom here, right? Total for pregnant is 50. So regardless of how they were tested, it's that you had 50 women that were pregnant and you had 450 that were not pregnant. All right, so I might get a little bit ahead of myself here, but I want to do one calculation with those. If you were to take the 50 out of 500 to find a percentage, like what percent is 50 out of 500? I can just divide these numbers, 50 out of 500, and that's going to come back. Hopefully you can see with the division already with the 5s on there, but I'll show it to you. We're going to get 10%. 50 divided by 500 is going to give us 10% or 0.1. Okay, so what this is actually called is the incidence rate. How many out of the total group that we looked at actually are pregnant, or if we're talking about the cancer one, would actually have cancer, if we're doing like a drug test or actually taking the drug. Okay, we call this the incidence rate. Okay, we'll come back to that stuff in a little bit. All right, the pregnancy test is 90% accurate. So this is sort of like the advertisement that goes with it. It says 90% of the time we're going to get this right. So in this case, what it means is that of the women who are pregnant, of just those women, so of those 50, 90% of the time it's going to get it right. Okay, and we're going to look at that calculation here. If we take 90% of 50, we're going to end up getting 45. Okay, and as a calculation, remember, all we need to do is change that to its decimal form. So we take 0.9, multiply it by the 50, and you get back 45. Okay, so 45 of those test results are going to come back as positive, which is correct. The other 5, which might actually be easier to see here, that 5 is 10% of 50. The other 5 are going to be false negatives. They're women who are pregnant, but it comes back saying that they're not. So that's where these two numbers come from. These numbers are done similar. Sometimes a test, its accuracy for being positive and its accuracy for being negative are different. In this case, they're just saying that there's a general like 90% for both categories, but you may see in some stuff a little bit later that you can actually have different accuracies depending on the two different categories that we have here. All right, so the math here is just going to mimic, though. You're going to take 90% of 450. That's just going to be 0.9 times 450. And and you get 405. So that would be that number. And of course, 10% of 450, you just move the decimal and you get 45. So that becomes our breakdown there. Now that we have the table built and we sort of figured out that structure, you use your accuracy rate from these bottom values to break this stuff up here. We're going to dig a little bit deeper into this, and we're going to try and understand how we should interpret the results. See, the thing about these tests is when they're advertised based on their accuracy, those are based off of the numbers that we have here. But what we have to keep in mind is that when the test is done, like when that's actually happening in the real world, real things are happening. A woman's taking a pregnancy test. She doesn't know if she's pregnant or not pregnant, right? What she's going to be relying on is the result that comes from here. So we don't know these values. We're going to be relying on these, and we want to know how much can we trust that positive result or that negative result. All right, so let's look at these questions. How many tests, from the information we're looking at, how many tests had a positive result? Okay, so that would be the 45 plus the 45, which is going to give you the 90. That would be the total number that had positive tests. Remember, only 50 women actually had it. And of that 9 have it, are pregnant. I'm still thinking of the cancer problems here. Only 50 of the women actually have a baby, but of course only even 45 of them were getting the right results. So you've got 45 who are getting positive tests that aren't pregnant. All right, so how many of those tests had a false positive? That's the 45, I just mentioned this right there. Okay, here's where it gets important. What percent of all positive results were false positives? Okay, to answer that question, you have to look just at the top row because it says of all positive results. So we don't care about anybody who had a negative result. We don't care about these two when that statement's being made. We're only interested in those who got the positive results. Okay, and that would be 90 of them. So of the 90, what percent were false positives? Okay, and here would be the general setup that we've been using in the class, which would be X percent of 90 is equal to 45. I probably should have written this part out somewhere, so I'll just add it to this spot here. But we have X multiplied, whoops, almost changed that in 2%. X multiplied by 90 is equal to 45. So if we divide 45 by 90, we're going to get our result for X. Generally speaking, if you're just trying to find a percent and you know the small amount and you know the larger amount, you can just divide those two. So you can just divide the 45 by the 90. Of course, 45 divided by 90 is going to come back as half, which is 0.5. So that means we're getting 50%. Okay, and now we want to digest this for a minute. The accuracy rate of the test, as advertised at the beginning, is 90%. Of the women who are pregnant, 90% of the time it's going to come back and say positive. And the same thing for that are not pregnant, 90% are going to come back as being negative. Okay, but when you start looking at the data that we really have, because we don't know this information at the beginning, when you start just looking at what we got were positive, negative results, it ends up that a positive test is only 50% accurate. All right, number 5, what we're going to do is investigate the negative tests now. Just kind of get a feel for that one. All right, how many tests had any negative results? That'd be 410. How many of those tests had false negative results? False negatives, oh, here they are right there. That would be 5. False negative, you get a negative, but actually were pregnant here, okay? So only 5 of those. These are all correct negative results. These are all the ones that are going to be incorrect. All right, so if we do the same problem that we just did above, really all we got to do is take 5 and divide it by 410. It comes back as a very, very small number of 1.22%. So where we look at false positives, over here, the false positives, and you're comparing that to the accuracy rate, you're going to notice that that is much smaller than what our accuracy rate would have been on there. So we You can't be as confident as you want to be in the test with it. All right, on the other end of this with the false negatives, that is actually a really, really small percentage, which means that if I almost kind of wish we did the calculation here. I'll show it to you though. If we take the 405 and we divide it by the 410, a negative result is going to be practically 99% correct. So you have the other end of this, that negative results you can be very confident it's the positive ones that we need to be careful about. All right, in problem 6, what we're going to be looking at here is just generally how to take numbers from the table and put them together to create the correct percentage that you're being asked for in the problem. The main thing in all of these is to try and figure out what the whole part is, the whole part. The way that I do the problems for this, they're all going to look like fractions as I go through them. The whole part is going to be the denominator. Okay, so in the past, we had done a lot of percent problems in this way because sometimes, because your x could be in any of these spots that you're solving for. But it does work out for the types of problems that we're doing here on these tables, that if you just set it up as a fraction, you're going to get your answers and you shouldn't really have any issues with it. So the bottom's going to represent the whole, the top is going to be the part, as you're used to with fractions. All right, A, what percent of pregnant women tested positive for pregnancy? Okay, so we really want to look for the word of. Now, sometimes there might be a wording that's a little bit different, and hopefully we'll be able to deal with those. But I believe here we're going to be able to look at each of these, and yes, that one will change a little bit. But a lot of the times you can look for the word of. Okay, so whatever's after the word of is going to be that denominator. That's going to be your whole part. So it says, what percent of pregnant women tested positive for pregnancy? Okay, so of pregnant women, there's two things that can happen. They can either test positive or negative. So we want testing positive of the pregnant women. So on the table, the place that you're going to look is just pregnant women. You're not going to look at not pregnant at all. You're not going to look at any of these totals over here. Just of the pregnant women, which is 50 of them, what number tested positive? That'd be 45. Okay, so we go back down here. Your fraction will then just be 45 out of 50, which is going to divide down to 0.9. The same thing as 90%. This question, you already knew the answer to because that's how we built the table like at the beginning. Okay, we didn't actually build the table what I talked about, like how you would do it. So we saw that calculation. B, what percent of women were pregnant? Okay, so what percent of women, not pregnant women, not because we're asking about pregnant. This is just of women, which is your grand total number over here. What percent of the 500 were pregnant? Okay, so out of the 500, the number that were actually pregnant were 50 over here, not to be mistaken with the number that were tested positive, right? So you're looking at that total, but now it's going to be in this row. Okay, so what percent of the 500 were pregnant? Well, there's 50 of them, so 50 out of 500 is going to give you 10%. I did mention that earlier. This is called the incidence rate. That is what the reality is, what the truth is, regardless of how those tests are coming back. So only 10% are actually pregnant. Question C, what is the chance that a woman is pregnant given that she has a positive test? Okay, so this one's worded a little bit different, but this is like your of part. Because in the others, we would say of your whole, of your whole, which would be the woman there. Okay, if we say given that, then this becomes your whole. This is actually pushing you into a certain row or a column that you need to look. So we need to look in the column or the row that represents positive test results. So what is the chance that a woman is pregnant if she has a positive test? Okay, so we go up here. We're just looking at that row. All right, what is the chance that she's actually pregnant? There were 90 positive tests and 45 that were not. By the way, this is going to look very similar to problem number 4, except 4 was focusing on the false positive, which was that number. So now we're looking at that actually are pregnant. The calculation's the same thing though. It's going to be 45 over 90, which comes back as 50%. Okay, question D. A positive pregnancy test means the chance of being pregnant is 50%. That comes from this answer here, compared to the overall incidence rate of 10%. To be honest, I keep trying to think about why we're putting these two as a comparison together, and I don't quite see that. So please don't focus too much on this compared to that part. Just be thinking about choosing the whole value and what the part is. And there's a whole bunch of other ones that you could be asked. One that I thought would have been neat to ask is, what percent of women tested positive? I think that one's a really neat one to look at. What percent of women tested positive? That would be 90 out of 500, which comes back as 18%. I think that's an interesting one because if our incidence rate is that 10% of women are pregnant, but our test results overall are coming back at 18% are, I think that sort of highlights the idea that we've got a lot of false positives in there. There are also some false negatives in there, and but it does definitely highlight that there's more false positives than there would be false negatives. All right, the second part for 3E, which is going to be Simpson's paradox, is another example of how we should be cautious about data that we're looking at. False positives and false negatives, all of that business sort of worked with like medical tests, like pregnancy tests, maybe drug tests, the cancer tests, stuff like that. This is a little bit different. The main idea about this, which is going to get broken down as we go through it, but I'll share it with you at the beginning here, is that when we collect data about something, it's possible to break it into small categories like that. So you see this all the time where there's generally like one big number that represents things. We call it the overall, and then you also have these small categories. And the problem is that even though you could look at all the small categories and they tell you one story, there's a chance that the overall story is different. That's what Simpson's paradox is. A paradox is something that doesn't really seem to make sense, right? So our small categories could all lean to one conclusion. We're about to see it here. They all lead to one conclusion, but the overall tells a totally different story. And it's just a weird thing that happens in the numbers. And sometimes you can pinpoint where it's happening. Other times it is a bit confusing. All right, so to begin here, what we're going to do is look at a comparison between LeBron and Tony Parker. Part A, we are looking at the shooting average during the first half of a game. And part B, we're going to look at the shooting average during the second half of the game. By the way, they don't really have that many shots on there because I remember this is a problem from the textbook. But I think the writers of this one just changed the names to people that you'd recognize. So LeBron probably had more, he probably took more shots than 10 during the first half of the game. Anyhow, just in case you noticed that on there. All right, in the first half of the game, LeBron made 4 out of 10 attempts, and Tony got 1 out of 4 attempts. So if you calculate the percentages by just dividing those numbers, you get 40% versus 25%. We asked this question, who did better than during the first half? 40% is better than 25%, so LeBron, he did better. All right, B, second half of the game, LeBron made 3 out of 4, which is 75%, and Tony got 7 out of 10, which is 70%. Who did better in the second half? LeBron did better in the second half. Okay, so then we pause there. We look at those two small group things, right? The first half of the game, the second half of the game, not the overall. And we come to the conclusion that LeBron did better, right? He did better in the first half. He did better in the second half. He did better. That's how we should say it. But if you look a little bit closer at the numbers and we just take an overall, don't break it into the two halves or just look at overall, and we start adding some numbers, LeBron had a total of 14 attempts, 10 and 4 together is 14, and he made 4 and 3, which is 7. So you get 7 out of 14 of those. You're going to notice here that Tony also had the same number of attempts, which was 4 and 10, giving you 14. But but he made 1 and 7, which is going to be 8. So if you calculate 7 out of 14 versus 8 out of 14, you're going to get 50 to 57%, which means that overall Tony did better. Contradiction. And that's what Simpson's paradox is that if you look at individual like subgroups, little chunks of it, in this case it was the first half and the second half, the data results that you get back from that might not represent the overall. Now, many times it does. I don't want to lead in a direction and say that that's never true, but a paradox is something that we don't expect to happen, and occasionally you get these weird things that the small groups don't tell the same story as the larger one that we have. All right, a little bit, the part that we're going to look at here is a little bit of a summary of what we just saw, and hopefully a chance to slightly justify why it can happen. The stuff is kind of tricky to understand where it happens in the numbers, but we want to get a feel for the fact that it can and why it might make sense as we go through it. All right, LeBron did better in each half. Tony did better overall. But let's just take a look at the halves where they had most of their attempts. The half where LeBron had most of his attempts was going to be in the first half, and that was where he did the 4 out of 10, so he got 40%. The half where Tony had most of his shots were going to be the second half, which was the 7 out of 10, so the 70%. And remember, he had the overall one. So now we're seeing that in the compared halves, that Tony matches the overall that we would have there. It doesn't completely explain why the numbers fall they are. That doesn't mean that this is a rule and how you would do it is like, well, don't pay attention to the halves that didn't have as many shots. Look at the one where you got most of the data, but in this case, it at least supports that we could be getting an answer at Tony for the overall. All right, at the top here, we have a definition for Simpson's paradox. A set of data may give different results for each of the several group comparisons than it does when the groups are taken together. Okay, kind of looked at all that. I don't think you need to break down too much of that. Okay, here's a neat question, and I wish we were doing this in class so I could see what everybody's answers are to it, because we just mentioned Simpson's paradox, all right? And then we give you this little question here and try and see what your response is. Well, the fact that we mentioned Simpson's paradox before, it means we want you to be critical of what you're reading. Okay, so the answer is going to end up being a no. All right, it says, suppose that a pharmaceutical company shows that a new medication improves a condition more than an old medication does in both women and men. Does this mean that the new medication necessarily works better than the old medication for the overall population, which of course is men and women? And I think before you know the answer to the question, if you were just hear that information, you would say yes. It's like, well, we tested men and women, right? We tested everybody that's out there, and if men new medication was better and women new medication was better, then yeah, shouldn't it be? And it's almost hard to figure out like why that won't be true. In fact, this question might be a little bit premature to ask because we need to see a little bit more practice work to start to understand where the issues might be in those smaller groups, like when we just looked at men and we just looked at women. Okay, here's the thought that I wrote to the side just to remind myself what I wanted to mention here. The problem, I didn't read my answer for this part, says, no, the idea of Simpson's paradox is to not let the small group results represent the overall, because there might be something that, I'm going to say it like this way, is unfair within your small groups. That might be the case that's wrong there. Like if you go back to LeBron and Tony, it was kind of unfair to do a comparison in the first half because he had a lot more attempts than he did. The concept of percents is to try and get them on the same playing field with them, but every attempt here for Tony was worth 25%. Every attempt here for LeBron was only worth 10%. So, when Tony would miss one, that hurt his overall worse. Okay, so So the thing that we need to understand is, are the groups the same size? And that's what's not mentioned in here. And we actually have 4 groups that are in here. Okay, at first you might think that there's only men and women and say, well, as long as we have the same number of men and women, then this should work out fine, right? You do 500 and 500 or something. Okay, but even within the categories of men, there's 2 subcategories: men who got new medication and men who got old medication. So you have that for the men, you also have it for the women, which means that you have 4 groups. And if those 4 groups aren't set up to be the same size, then you can get, misleading information from it. Question number 6 is going to have us look a little bit closer at the group size issue that I was just mentioning in number 5. Sometimes the group sizes are things that we can't control. Like in the pharmaceutical company, they should make all 4 of those groups that I mentioned the same size. But in other things, like what we're going to look at in 6, your group sizes are what your group sizes are, okay? And as you look at those results within just the groups, you can get things that are different than the overall because of that unbalance in the group sizes. Okay, what we are looking at is tuberculosis tests in New York City and Richmond, Virginia, in 1920. I know there's a date somewhere here. Okay, checking out the table. This is everything New York. This is everything Richmond. And what we did is we broke them into these 2 groups of white and non-white. Okay, white population, non-white, and we do that for both these. But we also have the total, just, the total population in New York, regardless of the race, and same thing over here in Richmond. All right, all of these calculations here. These might be a little bit odd with all the decimals in it because we have super large numbers, but let me show you like where the decimal place is supposed to end up here. Okay, so the percent, they don't want to hear that, 0.18 that I'm getting, that is going to be the number of deaths of whites in New York City divided by the number of whites in New York City. So we're totally taking out non-white here. Anyhow, the numbers are pretty large, and when you divide it up, you get this. As a percentage, you're going to move that decimal spot over 2 spots, so it's like multiplying by 100, which is going to get you to here. And then I even had a little bit of rounding that I needed to do. That 6 is going to change the 9 up to like a 10, which is now going to make that an 8. So it does round off to that number. So there's a lot that's happening in the calculations. I want to share at least that one. The rest of these, 500 divided by 92,000, 8,900 divided by this, 130 divided by 81,000, and so on through the table, and that's how we get all the numbers. All right, now what we want to do is start looking at some comparisons here. Which city had the higher death rate for whites? Okay, so we're talking about whites here. That means you're only looking at the top row for each of these. A higher death rate, a rate is going to be referring to anything that's got the division, so that's a percentage number. That means that we're comparing these 2 numbers. That one is just slightly higher. Remember, this is less than 1%. It's 0.18%, but it is greater than 0.16%, so that's going to be New York City. Okay, if we look at non-whites, next question here. In New York, you've got over 0.5% here, 0.543. And over here, Richmond, you've got 0.34. Okay, so they both are higher than what we were just looking at. New York wins again. Not that that's a prize you want, but they have a higher death rate there. Okay, so if you were just looking at those 2 categories by themselves, you didn't have the total one, we would probably say, okay, the TB death rate in New York is worse than it is in Richmond. However, if you take the totals here, right, so you add everything down across, and now we're dividing the total deaths, regardless of race, by the total population. Look at the comparison that we get. Richmond's actually higher. Richmond's actually going to be higher in that one by a little bit, but now it changes the story, right? So you can talk about in New York having a higher death rate in whites, having a higher death rate in non-whites, but overall it tells us, the table tells us that Richmond had a higher death rate in general from TB. Okay, so now what we want to do is try and figure out where that's coming from. It's a comparison of those sizes of the groups that we have here. All right, and it's really coming from the non-white categories that we're looking at. That seems to be the biggest difference in the numbers here. Like these two are pretty darn close to each other, and there's a little bit more. Anyway, if you calculate the percent of non-whites in New York, that's going to be 92,000 divided by this number, and you're going to come back with 1.93%. Now you go over to Virginia, and you take the non-white population of 47,000, you divide it by the total population of 128,000, and you realize that the non-white population in Virginia is a lot greater as a percentage, a lot greater than what we have in New York. Look at that, 36% over here. Okay, so maybe you almost need to imagine, like, if you're on the street and you're looking at people and, you know, you can see their different races, that this is, in 1920, is lots and lots of whites, not very many non-whites that you would probably interact with. Here, well, it's 36, so it's a little bit greater than a third. So a little bit more than 1 out of every 3 people would be a non-white. Okay, so how does that then overall change the data that we look at? These percentages were basically the same, right? Over here, that one's greater than this one, but these are also the numbers. These numbers compared to what we have for the whites are so much larger. What we want to see is the weighting that each of these receive. So even though the 0.5 is greater than 0.3, that 0.5 is, for such a small group of people, it's only, you know, it's about 2%. Their overall rate isn't going to receive much from that group. But here, since that death rate is coming from 36% of the population, that number ends up counting a lot more in the overall calculation, and that's how the total gets bigger. Okay, for question 7, this is a pretty short problem, won't really take that long to go through. The idea is that it's going to be Simpson's paradox, which means that your small groups are going to tell a different story than your overall group. That's what we're looking for in here. My opinion, the hardest thing that you're going to look at is just that the way everything is typed, it isn't organized that nicely, and you can get lost in all the numbers. So what I tried to do here was underline things. What did I underline here? Anything that's treatment A, I underlined in red, and then anything that's treatment B, I underlined in purple. The first 2 underlined, you know, as you go through the sentences, these are going to come from trial number 1. Then the next 2 are going to come from trial number 2. Okay, so in trial number 1, when you do a comparison of these, you got the 40 out of 200, and then you got the 30 out of 200. They're both out of 200, so that's kind of a fairness there. So you already know that A did better. The percentages that went with them, the 40 out of 200 was the 20. I don't want to underline that because it would get messy. Too many things underlined, but 20% versus the 15%. Okay, but we do see that treatment A did better in the first trial. All right, in treatment B, if you look at the numbers, it's going to be a little bit harder to compare based on what I'd underlined here, because you got 400 versus the 100 is there. Of course, right before them, you're going to see the percentages. So you got the 75% and 85%. So again, treatment A is going to be higher than treatment B. All right, so I ended up answering this question first, actually. Which treatment had the better cure rate in the 2 trials individually? That was A, for everything that I just talked about there. Okay, but being that this is Simpson's paradox that we're studying, what we want to do now is take the totals and do a comparison of that. So going back to what was underlined, if I just take the red ones, we're going to add the 40 and the 85 together, which will give you 125, and you're going to divide it by 200 plus 100, which is 300. So 125 over 300. Okay, treatment B, same stuff. You can take 330 when you add those. You're going to get 600. You get those. So 330 over 600. And then when you divide these, you get their percentages, which will come back as 41.7% and 55% there. So individually, we see that A did better, but in the overall comparisons, treatment B did better. And it's a little bit hard to pinpoint exactly where that occurred, but it has to do with the fact that the sizes weren't the same. I mean, you look at the denominators, they ended up having 600 people using treatment B, where they only had 300 people doing treatment A. All right, in conclusion, we talked about false positive, false negatives, and Simpson's paradox. There might have been a lot of things that I talked about that weren't as clear as possible, because where this comes from, it's a bit confusing to understand that we expect one result based on how it's advertised with testing or based on looking at small groups, and we get back something that's a little bit different. However, as we go through a little bit more practice on this stuff, it will begin to make a lot more sense of what we're looking to see here.